My name is Ángel Cardama. I am a professor at the Universidad Politécnica de Catalunya. In this unit, we are going to talk about electromagnetic waves. They are also called radio waves from the early times of science, of the radio times, of broadcasting, of radio broadcasting, and they are really just a combination of electric and magnetic fields that oscillate together. Light is also one wave of this kind. It's a very important one because we can see it with our eyes without any further help of gadgets or receivers. We will establish some of the basic aspects of those waves and see how they are generated and the way they propagate in space. There are many instances where we use those waves in our everyday life. Just to name some, we first have our phone sets that really just are examples of this kind of systems. We also receive TV signals by air, or we can access internet by a Wi-Fi connection. Those are examples of this kind of systems that use waves of this kind. They are really complex, and we'll try to see some basic aspects of them, but also they may be long range or short range. For instance, when we communicate through a Bluetooth connection, some gadgets or phones to our car, this is just a very short range connection. But when we receive the GPS signal on our mobile phone, the signal comes from a faraway satellite. In some cases, the size could be really small, as is the case of those phones, or could be large, as is the case of the radio towers that broadcast the signal to our radio receivers. We will try to see how those waves are generated and the way they propagate in space. And just to give you some hints of the historical background, here you have two pictures that you may well identify. On the left, Newton, and on the right, Maxwell. Newton puts forward all the laws that govern the mechanics of our world. And Maxwell did exactly the same thing with the electrical and magnetic problems. He also introduced light into the theory and proved that the light is nothing different to an electromagnetic wave. It belongs to this class. Newton, on the other hand, had already considered light to be made of corpuscles, and Maxwell have shown that they are waves. They both really have addressed problems that are of concern to man regarding what we may call the macroscopic or the real world, where the scale of the things are really large. And you should keep this in mind because of the laws we're going to talk about and the cases we are going to see are all related to very large scale things. If we try to go to the atomic level, what we may say the small world, then things will be quite different and we will be entering the quantum world. So we will be just staying in this macroscopic of large scale world in which we live. And we can learn a lot from this world. Here you have one example of something that is very familiar to us. This is a really powerful, couple of pictures of really powerful storms. And in all of them, you will see that there's lightning, and those thunderstorms really not only generate light, but also generate the strong electrical fields and also sound. It was clear for a long time that they were electrical in the sense that they could produce burnings and they really really damaged. They made a lot of damage to those storms. And in fact, it was due to Ben Franklin, the fabrication of the first lightning rod, just to try to attract electricity and discharge it to the ground. If you look at the lightning in these pictures, you will see that there is really flashes or bolts going down from the clouds to the ground and also from cloud to cloud. Really, in most of the storms, plenty of lightning goes from cloud to cloud. And the voltages involved in those lightnings are really of the order of hundreds of millions of volts. And also, quite similarly, the currents may go up to hundreds of thousands of amperes. So they are really strong in them. We can learn a lot from those images in the sense that you can see a current going down from the clouds to the ground, and you could also see that there is light coming from. It was also known that they produce a strong interference to the radio stations, and most of the power is concentrated at both optical frequencies and also at radio frequencies. The way the lightning goes down is because the air loses its character as insulator and all of a sudden becomes a conductor. Really, there's an ionic channel by which the lightning can go down to the ground. But there's something that we all know, is that the thunder that is accompanying the lightning, which is nothing more than the shock wave produced by this discharge, really reaches our ears with a delay with respect to the lightning. And that's due to the velocity of propagation of sound, which is really much smaller, it's about 1 million times smaller than the velocity of propagation of light. And here you have the second effect that is important to remember regarding waves, is that it takes some time to reach the observer from the moment it was produced. When we just receive the light from a distant star, then really the light we are receiving was produced a long time ago, and it has taken a lot of time to travel to us. In this case, the distances are small, and the velocity of light is so high that to us it seems to be instantaneous, but that's not the case. There's always the velocity of propagation involved. And Maxwell has to be also credited as establishing that velocity of light as the general velocity of all electromagnetic waves. Before going into the Maxwell domain, let's honor briefly Newton. And here you have the basic law of gravitation. In this case, we have two bodies, the Earth and the Moon. You can substitute it by any other situation. It could be a satellite, or it could be any one of us just staying on the surface of the Earth. What happens when you have two bodies and the masses of the two are represented here on the case of the Earth by capital M and on the Moon by lowercase? We know that the law of gravitation will really exert an action, is our weight in our case, and we have to represent those forces, in this case from the center of the Earth and the Moon, if were the case, would be from the center of masses of the body, and there is an attraction force that is really the same in the case of the force exerted by the Earth on the Moon that in the case of the Moon exerted on the Earth. The only difference is the orientation, the direction, which are opposite to one another. The law, and you should keep this in mind later on because you are going to see in the electrical world exactly the same kind of expression with different things written here, but it's going to be exactly of the same kind, tells you that the force acting on a body is proportional to the product of the masses and inversely proportional to the square of the distance that separates your centers. In this case, is that distance. N times a constant, which in this case is the gravitational constant, that has this number. You should also compare this number later on with the number that will appear in the electrical force case. Now, in this image you have here, you will notice something that will be used all along this class, this course. We have put an arrow on top of this F. This means that this is going to be a vector. A vector is just not only a number, as in the case of those, but also has direction, which is, in this case, is this force. And this force is pointing to somewhere. You will see here that there is also an R with a hat on it. Now, this is going to represent a unit vector, a vector whose magnitude is just 1. And we will use this notation for unit vectors along the course. N is pointing, in this case, R is pointing from the Earth to the Moon. It could also be pointing from the Moon to the Earth. If we use this, then we will have here a minus sign. In the next talk, we will be briefly reviewing those vectors and the scalars and those numbers, the basic properties of those vectors, of those things, and trying to find out how they behave and how we should establish some basic rules for them.